Yeah.
Yes, sir. You can start now. Sir, you're live now, sir. You can start speaking, sir.
Yeah. So welcome to all of you. So if you have any questions, can you start? So is it questions that will come in the chat box or will they ask?
Oh, the questions come, sir, on YouTube, sir. YouTube
Oh, YouTube,
chat
but
box.
can I see the
Yes.
YouTube chats?
You can open the other window, sir.
Oh, okay. Let me see. Okay, okay. Yeah, I just opened the Zoom actually. That's why.
Questions
Yeah.
come, sir, on YouTube, sir.
Okay, okay.
YouTube
Oh,
chat
YouTube, but
box.
can I see the YouTube chats?
You can open the other window, sir.
Oh, okay. There is a separate link on Achinto. Yeah, I just opened the Zoom actually. That's why. Yeah.
Come, sir, on YouTube, sir.
Okay, okay. Oh, okay. But can I see the YouTube chat?
You can open the other window.
Oh, okay. There is a separate link on Achinto. Yeah, I just opened the Zoom actually. That's why.
Come, sir, on.
Okay, okay. Oh, okay. But can I see the YouTube chat?
You can open the other window.
Oh, okay. There is a separate link on Achinto. Yeah, I just opened the Zoom actually. That's why.
Come, sir, on.
Okay, okay. Oh, okay. But can I see the YouTube chat? Yeah, so they are saying there is a separate form. I don't know why this is repeating. Why is this repeating all the time?
Sir, put off your YouTube audio, sir.
No, Anik, excuse me. Anik, Anik Mukhopadhyay. Form. Huh. There is a separate form. What is that form? We don't have the form. Huh? Why is this repeating all the time? That's what I don't understand.
Sir, put off your YouTube audio.
No, Anik, excuse me. Anik, Anik Mukhopadhyay. Form. Huh. There is a separate form. What is that form? We don't have the form. Huh? Why is this repeating all the time? That's what I don't understand.
Sir, put off your YouTube audio.
No, Anik, excuse me. Anik, Anik Mukhopadhyay. Form. Huh.
Hello, sir. Sir, sir, can you hear me?
Hello,
Yes, sir.
hello.
Yes, sir.
I don't understand what's happening.
Sir, you speak, sir, something.
Hello, sir. You are not audible, sir.
Hello,
Yes, sir.
am I audible?
Yes, yes. Now you are audible, sir. Sir,
But
you have to solve the response sheet question, sir.
where is the response sheet? Have you sent
I
us
just sent you. Yes, yes. I just sent you.
by email?
Yes, yes. On email.
Oh, okay. Is Professor Datta also there?
Uh, Not yet joined, sir.
Okay. Yeah, so can we start?
Yes, yes, yes.
So question one, am I audible?
Yes, you are audible, sir.
So do I have to unmute myself in YouTube also? No.
No,
I
sir.
muted myself in YouTube.
Yes,
Yeah,
yes.
so
No need to unmute, sir.
okay, fine. So first question is what are MP2 natural orbitals? I hope the participants are able to hear me. Okay. So can we somebody write in the YouTube that are you able to hear me? Hello. Hello.
Yes,
Okay,
sir.
now
You
now
are audible, sir. You are
yeah, now it
properly
is clear.
audible, sir.
Yeah, so fine. So now it's clear. I got a green signal from Anik. So let me see the first question. First question is what are MP2 natural orbitals? How exactly do we find? So all natural orbitals are basically the eigenfunctions of the first order density matrix. So Anik, you might be knowing what is density matrix. Density matrix is not density, but it is the matrix which has off diagonal elements as well. It's in a Hartree-Fock approximation, its diagonal elements are the uh, very simply the orbital star times orbital sum over all the orbitals. So that is electron density. But you have a density matrix which is basically obtained from the full wave function by integrating over all the n minus 1 orbitals, n minus 1 electrons in psi star psi, keeping one psi star r prime, one let's say r. So then this gives a density matrix gamma r prime r, which you can expand in a or any basis set to get the matrix form. This is a coordinate form, matrix form. If you diagonalize that matrix, you get the eigenfunctions which are called natural orbitals. So the same thing in the Hartree-Fock sense, the natural orbitals are Hartree-Fock themselves, Hartree-Fock orbitals. So you don't need to do anything. So with the MP2 wave function, you can similarly calculate the first order density matrix and then you can diagonalize it so that you get the natural orbitals. So they are not very difficult. And with those natural orbitals, you can do further electron correlation problems, which simplifies. Like you can do large CI. First, you can do small MP2, get a small natural orbital, then using that and some virtual orbitals which are orthogonal to that, you can do a large CI. You can do large couple cluster and so on. So natural orbitals are very good because they help you to converge faster. So that is how MP2 natural orbitals are obtained. So because MP2 also has a wave function, right? It is the Hartree-Fock plus singly plus doubly excited determinants. So with that wave function, I can get density matrix. And then you can diagonalize, you'll get MP2 natural orbitals. So if there are any further question, Anik, then you or anybody, I don't know who has asked. If it is Anik, he has my number, he can call me. I will explain to in telephone because this is not interactive. So I'm not understanding whether you understand or not. The question 2 is I'm not able to read. While dealing with dynamical correlation, what is the full question? Yeah, so your first question also had one more part. Within the ORCA implementation of CAS-SCF, it is as right that MP2 NOs are better starting MOs than Hartree-Fock. Yes, that is true. Because it is MP2. Why MP2 natural orbitals are better than Hartree-Fock? Because MP2 natural orbitals are already correlated. It is coming from a density matrix, which is much more accurate than Hartree-Fock. So now if you start with that, if you do CAS-SCF, you will much more quickly converge. So that is the reason MP2 natural orbitals are better starting MOs. And Hartree-Fock, of course, MOs themselves are natural orbitals. So you don't need to do anything. Question 2, while dealing with multi-reference dynamical correlation methods, we encounter phrases like fully internally contracted or strongly contracted, like in the NEF-PT2 implementation of ORCA. What exactly is being contracted? Contracted essentially means it's a linear combination. So within the active orbitals, they make a linear combinations, and that entire function is called a contracted function, internally contracted function, or strongly contracted function. That means the basic active orbitals have all been taken care. Okay, so that is a multi-reference problem, because when you take configuration mixing, that is basically a multi-reference problem. And if you start with that and then do a dynamic correlation, PT2, etc., you will get very good results. So I hope I'm able to cut thing. Instead of starting from a single determinant, basically if you start from a multi-determinant and then do PT2, the results will include both static and dynamic correlation, right? So this multi-reference part is now called fully internally contracted part, a strongly contracted part, because then it can easily do a dynamic correlation and the results will be much better in terms of both static and dynamic correlation. So that is the reason it is done. So contracted essentially means it's a linear combination in a very simple term. And there is a phrase called contracted. I think Professor Achintya Dutta, I don't know if he has joined.
Yes, I'm here.
Yeah, so can you elaborate in it? But I believe we have done some work on this.
So you have to, can you please repeat the question again? I'm sorry, I got a little late.
Question is, while dealing with multi-reference dynamical correlation methods, we encounter phrases like fully internally contracted or strongly contracted, like in the NEF-PT2 implementation of ORCA. What exactly is being contracted here?
So if you think of single reference method, the framework is very clear. It's it's a perturbation operator or the cluster operator which is actually bringing in the correlation effect. Now remember, in this multi-reference method, the correlation effects are bring by two ways. One is the so-called the CAS-SCF operator, where what you are doing is that you are doing basically a full CI calculation within a restricted active space. So now that full CI operators also brings you a part of the electron correlation effect. Now, when you are doing a perturbation of thing, the PT2 or the MRCI, now the CI operators also brings you the correlation effect. So now what happens in many of the cases is that you have more number of equations than you have variables. So that means there is no unique way of determining it. Now, what you can do here is that you can restrict your variable space by considering, can this operator contract among themselves? And that allows you to actually give you a proper number of equations. And that's how the definition comes. It's a strongly contracted or fully internally contracted. Remember, in a normal couple cluster method, the cluster amplitudes cannot contract among themselves. They will only can contract with the Hamiltonian. But that's not the case when you have operators which are belong to two different way of bringing the correlation, like the CI operators which you are using in the CAS-SCF and the CI operator which you are using in the MRCI, they are completely different things. Now, question is that can they be contracted among themselves? Yes, you can consider them to be contracted, or you can consider them only a selected part of them to be contracted among themselves, or you can consider them to be totally decontracted. That would lead to different answers. Remember, these different answers only matter when you are working with a when your complete active space is not the full space, as well as your CI operators are limited to like a CID, or maybe the quadruples are included like that. If you are doing full CI or you are doing a full complete active space, then none of this actually matters. But if you are doing a limited space, then they will lead to a slightly different answers. In most of the cases, your rule of thumb is that if your cases, in the case of CAS-SCF, if your occupancies are between 0.9 to so for the occupied orbital, if the occupancies are below 0.9, then most of the cases there may be some problem, and in that cases CAS-PT2 may not be a good option. Remember, this CAS-PT2 or the MRCI based method, they are actually correcting for whatever is missing. That's the dynamic correlation part, and PT2 is actually only the perturbational guess. So the CAS-PT2 will only work when your like CAS-SCF results were almost there and you were missing only a part of the non-dynamic part of the dynamic correlation. Whereas in MRCI, because it's solved variationally, they are much more robust. And in that case, which versions you are using, the internally contracted or strongly contracted, does not matter so much. So for MRCI, in most of the cases, they work well. At the same time, which version you are using, it also have a lot of effect in the computational cost. So most of the cases, the fully internally contracted ones actually has the least of the computational cost, but it's much more difficult to implement. And actually, to implement this fully internally contracted by doing a normal programming, like deriving the equation by hand or writing the program by yourself, is practically impossible. So most of the cases, these fully internally contracted methods are, the equations are generated by generally by some expression generator, and the programs are generated by the automatic code generator. So in Orca or in MolPro, which are considered to be good MRCI programs, none of them, like the programs are hand coded. They are actually automatically generated by computation cost by using a computer generator.
Yeah. There was a question one, which before you came I answered, but you can elaborate if you want. What are before I go to question 3, there is a third question. What are NP2 natural orbitals? How exactly do you construct them after doing NP2? Within the Orca implementation of CAS-SCF, it is as advised that NP2 natural orbitals are better starting MOs than Hartree-Fock MOs. Why is that the case? So I actually said that is because it has included correlation, etc. And what are natural orbitals? So if you want to elaborate that question.
Yeah.
So how do you construct them within Orca?
Yeah.
How do you first construct them after NP2? And within Orca, it is advised that NP2 NOs are better. Why is it so?
Okay. So I think Dr. Pal has already answered most of the parts. I just wanted to make this very simple point. So the natural orbital is actually a one particle representative of a multi-determinant wave function. It's basically, when we think of, let's say, molecular orbital picture, we are still working with a single determinant that our mind can conceptualize. One electron in one orbital, and then I take a linear combination of them and symmetrize. But when I have multiple determinants, to think of the electrons in terms of orbital is not very helpful. You cannot really conceptualize, visualize in your mind. At least I cannot visualize in my mind. So natural orbitals are basically a one particle representation of a multi-electron determinant. And They are called natural because they are more close to the exact wave function. So now question is that to how you get the natural orbital. Natural orbitals can be obtained by by any electron correlation method, which actually gives you a multi-determinant picture. Why we use MP2? Because MP2 is the cheapest of the electron correlation method possible. So after you calculate the MP2, and MP2 is a special case where the MP2 Hamiltonian is actually Hermitian. And so you can calculate the density after the MP2 step, you can calculate the one particle reduced density matrix at MP2. And if you diagonalize them, the eigenvectors will give you natural orbitals, and their eigenvalues will give you the occupancies of this natural orbital. Now, getting a natural orbital is no way better than a normal Hartree-Fock orbital in most of the cases, because the natural orbitals are actually the way, of course, it depends upon how the natural orbitals are generated. In most of the cases, the occupied and the virtual blocks of the natural orbitals are diagonalized separately. So basically, they are an unitary transformation of the original Hartree-Fock orbital. So if you are using, let's say, if I am doing a couple cluster method on the entire basis, so it does not really matter if I am, or a couple cluster of Ci on an entire basis set, like entire set of occupied and virtual orbitals in your basis set, it does not really matter you are using Hartree-Fock orbitals or natural orbitals. But when you truncate, then they lead to different answers. And just think what CAS-SCF is. CAS-SCF is actually a restricted full Ci. So where you are considering your full Ci calculation within a certain active space with certain number of occupied and virtual orbitals. In that case, the natural orbitals will give you a different answer than the normal Hartree-Fock orbital. But the cases where you are doing a untruncated calculation, and you can check it by taking a small system in a small basis set, and you can use all the orbitals and all the electrons are active. Maybe you can do, let's say, HF in STO3G basis set. So that will essentially a full Ci. And in that case, you will see that does not matter you are using Hartree-Fock orbitals or natural orbitals, they will lead to exactly same answer. Now, why people advise you to, now this only explains you that the natural orbital will give you a different answer than the normal Hartree-Fock orbital. But why people advise you to choose the active space in CAS-SCF? Now you need to think what are the virtual orbitals in Hartree-Fock. So virtual orbitals in the Hartree-Fock is something which is basically can be considered as the garbage of the Hartree-Fock. So what you are doing in the Hartree-Fock, you are just optimizing your occupied orbital. So whatever bad was there in the occupied orbital, you are just pushing it into the virtual orbital. So Hartree-Fock virtual orbitals are very ill-behaved, and they does not have any information about the actual bonding of the molecule, because remember the actual picture, the actual experimental picture also includes the electron correlation effect. So to get a proper description of the virtual orbital, you need to have some kind of an electron correlation method. So that's why it's advisable to start with an MP2 natural orbital. Some people say that DFT orbitals can be also good. I don't subscribe to that kind of behavior. But if you use MP2 natural orbital, you get a very good description of the virtual orbital, which are more close to the exact description. So you can choose the orbital more efficiently. Eventually, finally, it goes to your selection, what kind of orbital space you are selecting. But MP2 helps you to do a good selection because these orbitals are more close to the exact orbital picture. That's why it's always advisable to use MP2 natural orbital in doing CAS-SCF calculation in any other methods. Remember this CAS-SCF, this CAS-SCF methods are not black box. It's actually requires a lot of chemical intuition you need to have. Whereas the single reference method, like a DFT or single reference couple cluster, that's completely black box. If you have sufficient computer power, you do not really need to think about anything. You just put the keyword and the software will give you an answer. You can trust the answer blindly. Whereas in CAS-SCF, the answer depends upon what kind of active space you have chosen. And if you have chosen a wrong active space, you can have answers which are qualitatively wrong. So one need to be very careful while doing CAS-SCF calculations. I hope this clarifies some of the doubts.
Yeah. So essential idea is that they are already correlated, these natural orbitals. And natural orbitals are always good starting point because it takes care of the full wave function, and which is in this case MP2 for the question 1. So it eventually is a better starting point to do a larger calculation. As I told you, many people do small calculations to get NO and then they scale it up for larger molecules, larger calculation because it converges much faster. Okay, so there is a question 3. If the standard couple cluster has the converged artifact MOs single determinant as its starting point, how can the excited state variant of it, that is UMCC, also model non-dynamical correlation is having multiple single determinants as a reference and not a prerequisite? So he has put a source of annual reviews. So it says that the standard couple cluster has converged Hartree-Fock MOs as a single determinant starting point. Excited state variant of it, that is UMCC, also model non-dynamical correlation is having multiple SDs as a reference and not a prerequisite. Not a prerequisite, it says. So do you want to answer anything to, because I'm aware that the UMCC has a version which starts from single reference, makes a standard couple cluster, and then generates the excited states from there. So in that sense, there is a multi-reference part in the excited state, but it is still starting from a single determinant and it is then generating through the whole particle excitations, the multi-reference part. So the non-dynamical correlation is also generated. So the first part is the standard couple cluster for the ground state, and then it generates the multi-reference part by various single whole particle excitations. And that generates the non-dynamical correlation. But he says as a reference and not a prerequisite. That I don't quite understand what this does mean. Can you see the question, Achintya?
Yeah, I can see the question, even the meaning is not very clear to me.
The
Okay,
last part, that he's having a multiple SDs as reference and not a prerequisite. That's the part I'm not quite understanding.
Okay, so in a sense that couple class, the equation of motion can take care of the multi-reference situation. It's not a very strictly correct thing. The IP and EA variant of the equation of motion can actually take care of the multi-reference situation because of the fact that they are actually identical with the Fox, the so-called multi-reference Fox space couple cluster, where Professor Pal is an expert of. And actually, you can show that the equation of motion is nothing but a rederivation of the Fox space couple cluster. Remember, the equation of motion couple cluster by construction is essentially a single reference method. And whenever there is a multi-reference situation, if you are starting from a case where your number of electron is not changing, let's say for an excitation process. For example, if I want to take care of an nitrogen molecule, I start with the singlet nitrogen and I calculate the singlet or triplet excited state of nitrogen molecule. If you stretch the bond a little bit, which is a typical multi-reference case, the equation of motion does not actually work so well for this kind of system. Now, what you can do in the equation of motion, you can actually include the multi-reference by doing a backhand kind of approach. What do I mean a backhand kind of approach? I can actually start with an N22 plus. And then I can add 2 electrons by using this double electron attachment variant of the equation of motion. In that case, it actually can give you access to the multi-reference states. But when you are using these particle conserving versions of the equation of motion, in that case, it's not possible to have non-dynamic correlation within the equation of motion. An alternate way of including the non-dynamic correlation is to use the spin flip variant, which Anna Krylov pursues, which essentially means that you start with the triplet state and while exciting, you flip the spin of the electron. That can generate a part of the multi-reference situation. But remember, this kind of tricks are not always very helpful when you have a real multi-reference situation like transition metals, or you are breaking a triple bond, or you are dealing a molecule like ozone and trying to break the bond. They are not very helpful. Equation of motion, at least the excitation energy variant of it, make no mistake, it's a single reference method. It is nothing but a single reference CI over a couple cluster similarity transform Hamiltonian. So it's just a single reference method. because you are doing over it a couple cluster, that does not really brings in the multiple determinant. The couple cluster is used for a different purpose, and one can discuss about it, but the straight answer is that it's a misconception that the single reference equation of like normal equation of motion can give you access to multi-reference state directly. You can get it by playing some trick, but it's not a general recipe. So for that, you need to go to the so-called real multi-reference method like Fock space couple cluster or Hilbert space couple cluster, where you can directly access the multiple determinants by construction. I don't know if Dr. Pal wants to add something.
Yeah, no, so just as he said that only for single hole, single particle problems, this so-called Fock space method turns out to be similar to the UMCC, but not for the excited states. We are talking about excited state variant. So they can be different. So indeed, but his question is that how does it model the non-dynamic correlation? So I thought the short answer would be because it has on the top of the couple cluster, it has the whole particle excited operators. So that whole particle excitations actually brings in some kind of multi-reference component. And depending on how many such operators are there, I think the quality of the excited states will be determined. So, but I didn't understand the part that is having multiple single determinants as a reference and not a prerequisite. So these are part which is not very clear to me what he meant actually. But yeah, it certainly models the non-dynamic correlation. So what he's asking, how does the UMCC model the non-dynamic correlation? That is essentially he's asking.
Okay, so here's a tricky part is you need to understand the difference between the contribution of the Hartree-Fock determinant and the singly excited and the doubly excited determinant to the ground and excited state. General consensus is that for ground state couple cluster, it's the double excitation which brings the correlation and the single excitation which brings the orbital relaxation. But if you think of excited state, let's say I consider equation of motions in singles and doubles approximation. So the singles part is like a CIS, it's configuration interaction singles. So that gives you the zeroth order approximation to the excited state. So in the case of excited state, the singles does not bring you any orbital relaxation or the correlation. Singles just provide you the determinant, like the excited determinants. So like the CIS is like a Hartree-Fock for the excited state. Actually less quality because it has a linear parameterization. In the case of it's the doubles operator which actually brings you both the correlation and orbital relaxation in excited state calculation. So the meaning of singles and doubles is very different from what you see in a couple cluster and an equation of motion. And one of the problems in the equation of motion is that you are having a CI-like linear operator. So that cannot take care of the orbital relaxation in a very effective way. Whereas in the case of ground state, you have an exponential operator which can take care of the singles, which can take care of the orbital relaxation in a very good way. So in most of the cases, singles actually removes majority of the problem which you have with your Hartree-Fock determinant. Okay.
Yeah, so
the question meant the UMCCSD start from a single determinant, but still somehow also model the dynamic correlation. It depends upon which kind of equation of motion you are talking about. You are talking of IP, EA, DIP, DEA, or the single simple equation of motion for excited state.
Yeah, there is another question by, I think, Prajwal. What are explicitly correlated methods? I tried to go through some reviews, but the material seemed to be a bit too advanced for a third-year undergraduate to grasp. Could you please give a brief introduction to what they are and how the features like accuracy, time complexity, size extensivity compared to the conventional method like CCSD, MP, etc.? And in what quantum chemistry codes have they been implemented in case you want to try them out? Yeah, so explicitly correlated methods. See, normally if you see all the standard quantum chemistry methods, they use the basis sets, right? So mostly atom-centered basis sets, and that's how they those virtual orbitals generate the correlation. But in the explicitly correlated methods, the correlation is used explicitly by a function, which is basically a function of a pair of electrons, like the what is called R12, that is the difference of the R1 minus R2 vector. And of course, the R1 and R2 itself. So it's a 2-electron function. Explicitly with this 2-electron pair function, the pair correlations are generated and not through the virtual orbitals. And this can be extended further, of course, beyond pair. But the point, yeah, it is not a very advanced thing. So we don't teach. We didn't teach in the NPTEL course, or we don't normally teach. But the point is that because we are not using virtual basis sets, in very big summary, there is a lot of problem of electron correlation which are basis set related. That means the basis sets have to be very large to give you good results. And we really can't. So it's a very slow convergence normally. And that is where I was telling that maybe natural orbitals will be little better in terms of convergence. But normal Hartree-Fock MOs that we use are very slowly convergent. The virtual orbitals are really bad. Bad, basically. So explicitly correlated function, because it allows R1 and R2 in the wave function itself. Okay, so it is not written in terms of orbitals in the standard sense. So what happens is that the electron correlation part, which is basically the fact that if 2 electrons come very close together, they must repel. So that is basically the effect of electron correlation, that whenever the difference between R1 and R2 will become very small, the wave function, the electrons must repel. And that effect is very nicely taken care in the explicitly correlated method by choosing a proper function of R1 and R2. So this is the, they call it F, sometimes they call it U, and this can be integrated within the couple cluster, within the other ab initio methods where the virtual orbital space is basically replaced by these explicitly correlated methods. So in some sense, the convergence is very fast. Convergence is very fast, but it involves a lot of complicated integrals. Integrals involving these R1, R2, etc. And even with a small amount of expansion, because this is not a single expansion, you not only take the power, just the R12, the difference of R1 and R2 is called R12, but also powers of R12, powers of R1, powers of R2. So the integral evaluation becomes very complex. So by any means, the coding is not simpler, but certainly the convergence, you can get a faster convergence than the normal virtual orbital basis sets. And that is the reason it is advocated. It is also very accurate for the same reason, because you can get the results very well. I don't see any problem of size extensivity compared to the conventional CCSD method. So it is also size consistent. And in what quantum chemistry codes, this I can't immediately tell, but there must be some codes where explicitly correlated methods are, maybe Achintya will know if there is software where these are actually implemented already. Achintya, would you like to comment on this?
Yes. So I think what I have to add to Dr. Pal's thing, that why explicit correlation is such a attractive topic to talk about. Just think what is a problem in the standard quantum chemistry calculations we are doing. My atomic orbitals are supposed to be a Slater. But of course, I'm not writing my equations in terms of Slaters. We are finally changing into Gaussian. What the major problem it brings? So the major problem is that in the Slater, the wave function should have a cusp in the nucleus. That cusp is generally not very well represented in the Gaussian. Of course, you can solve the problem by using a huge number of Gaussian. And if you choose the combination parameter properly, eventually you will be able to represent as cusp in the nucleus. And that's what happens in wave function based method, your results converges very poorly with respect to the basis set because the cusp are not properly represented and you need a huge number of basis functions to represent them. So what is done in this R12 theories is that you add terms which are explicit, which actually can take care of this explicit distance dependent. So the nuclear cusp is very properly represented in this kind of theories. Because they are properly represented, you do not need gigantic size of the basis set to represent the cusp, and your methods actually converges very slowly, very fast with respect to the basis set. So in most of the R12 calculation with respect to the triple zeta quality basis set, you can get results which are similar to quadruple zeta, pentaple zeta in a normal calculation. So that's the good part. The bad part is that, as Dr. Pal described, you need to have these additional terms and you need to derive those integrals. Sometimes they're called F12 and R or R12, depending upon you are taking linear or non-linear terms. This can be very expensive. So in most of the cases, an R12 calculation with triple zeta basis set may be of similar computation cost as doing a normal calculation with quadruple or pentaple zeta basis set. So unfortunately, there is no free lunches in this life. And if you gain in one place, you have to somewhere pay the cost. If you are interested in doing R12 calculations, I know ORCA definitely has R12 implementation for MP2 couple cluster, CAS, NEPPT2, MR. I don't think they have it for MRCI, but at least for NEPPT2, MP2 and couple cluster, it's there, including their DLPNO version. If you are ready to buy the software package, I think then a good option will be MolPro. There, I think even Molcast has a part of it. But if you ask me a ready and easy to go software, I will prefer towards ORCA. It has all the F12 modules, and these are coded by Edvalib actually.
Yeah. So that is fine. So I hope, but this is indeed a very advanced topic. So this is not certainly something that we like to advocate that you have to learn now under the NPTEL course. But this is a topic where very few people are working, I must say. But it is certainly worth doing research on this. Whether it will really survive in relation to the normal orbital based methods is something I think yet to be seen. I'm not very sure how much popular it will become. But as Achintya said, there are codes being written, the codes will become more easily accessible, and the results are good. I don't know if there is a very systematic comparison with the basis set on the virtual orbitals, which are Gaussian basis set best in terms of precision and timing. That is how quickly you can get better results for what systems, that I'm not very sure. It also may depend on what systems it is. If it can be scaled for larger systems, it will be certainly very, very useful. But once again, for larger system, the end dependence will certainly increase very significantly. And that is still going to be a problem, I think, in terms of computing time. But indeed, I thank you for your interest. I think it's Prajjal, the student's name. It's quite an advanced interest, I must say. And we'd expect that you will look at the progress of the method very carefully as it happens. And there are a few groups who are working very, very seriously on this topic. So I'm sure as you grow up, if you take up quantum chemistry as a research, it will be very good. Okay, so I think we are done with all the questions.
Yeah, and I think the moderator told that we only have 5 minutes left.
Yeah, that is true. But is there any more question? I think we are done with the questions.
I think
also.
we're done with the question.
Yeah, we're done with the questions. Yes. So this Prajwal is from ISA Trivandrum. And if I remember, Anik is also from ISA Trivandrum. Yeah, thank you. Very good. I think a lot of interest I see, because the questions are quite advanced. So it is good, quite good. And it's straight from research. Yeah. Okay, I'm done. See, Achintya wants to conclude by saying anything.
Yeah, thank you for your interest. And I'm as Dr. Pal said, we both are very happy to see that people are really interested in wave function or electronic structure theory method development, because the questions you have asked is very advanced. I'm sure nowhere they are taught. That's what you learn in your research. But I will advise you, it's continue your interest, learn about more advanced topics, also learn programming, because once you program these methods, your concept become much more clear and you understand many of the concept more in depth. So please keep in touch.
Thank you.
Thank you very much.
Thank you very much. Yeah. Thank you.